Greetings, Mathophiles. Welcome to the second in a series of two videos on integration by substitution, also known as u-substitution. In the first video, we gave an introduction and an explanation of the process, and we worked some examples involving indefinite integrals. In this video, we'll be taking a look at definite integrals. So basically, this is going to be about how we handle the limits of integration. If this is your first look at substitution, you may want to go to the first video before you take a look at this one so you have some sort of conceptual background about how this process works. We're going to work two examples, and we're going to work the first one in each of two ways so you can get a sense for what the options are and sort of make an informed decision about which one you might want to be employing routinely. So here is our first example. We wish to evaluate the integral from 1 to 4 of 1 plus root x all cubed divided by the square root of x dx. Now, one option in this would be to expand the cube, collect like terms, divide by the square root, and you'd have a sum of some rational powers of x, and you could go ahead and integrate term by term. But I'm going to suggest to you that it may be to your advantage to employ a substitution instead. So I look at this integrand and I see that the 1 plus root x is plugged into the cubing function. So we have the kind of composition that's characteristic of situations where you might want to consider substituting. And so I ask myself, all right, what's the derivative of that thing inside the cube? And the answer is it's 1 over 2 root x. And except for the 2, we have a root x in the denominator. We can engineer a 2 in the denominator. We just have to also introduce a 2 in the numerator so that we keep it square. What we're going to do in this first method is to evaluate the corresponding indefinite integral. Once we have an antiderivative of our integrand, then we can go back and plug in the limits and subtract a la fundamental theorem part 1. So let's evaluate the indefinite integral 2 integral 1 plus root x all cubed over 2 root x dx. And we make our substitution. We, of course, have the 2. And then that 1 plus root x cubed, that's just u cubed. And the 1 over 2 root x dx is du. And I guess I really should have written this somewhere. So our u is 1 plus root x. Our du is 1 over 2 root x dx. So it might help you to verify that our substitution was correct. Anyway, this is an easy antiderivative. We've got the 2. We've got 1/4 u to the 4th plus a constant. Reduce the fraction. Go back to the original variable of integration. So u is 1 plus root x. And there is our indefinite integral. Now, let's go back to the definite integral. We know that 2 integral 1 to 4, 1 plus root x cubed over root x dx is equal to 1/2 quantity 1 plus root x all to the 4th from 1 to 4. And what is that? Well, we've got the 1/2. And then if we plug in a 4, 1 plus the square root of 4 is 3 to the 4th is 81. We plug in a 1, 1 plus the square root of 1 is 2 to the 4th is 16. 81 minus 16 is 65. And so this is 65 halves, or 32.5. And so let's remember that as we then begin to approach this by means of another method. But before we move off of this, I have to issue you a pretty important caution. This object is a real number. We actually now know that it's the real number 65 halves. This object, this indefinite integral, is equivalent to a family of functions all differing by a constant. Obviously, very, very strong similarities, right? Visually, except for the presence or the absence of the limits of integration, they look the same. We have the same antiderivative-derivative relationship floating around, but they're fundamentally different sorts of objects. You don't want to stick one of each of those on opposite sides of an equal sign, because you're claiming that a real number is equal to this whole family of functions over here, and it doesn't make sense. It's an easy error to make. You need to train yourself not to make it. The equal sign doesn't mean here comes the next thing. The equal sign means these two quantities, the thing on the left and the thing on the right, are identical. If you're an AP student, the AP readers call those linkage errors, and that you lose credit for them. So be aware of that. Here is the same example, and we're going to take a little bit different approach to evaluating it. Same integral, we're going to make the same substitution, we're going to insert the same extra couple of constants to make everything all work out. The difference is we're not going to go off and think in terms of indefinite integrals. We're going to stay strictly in terms of definite integrals, which, if it doesn't do anything else, puts us in a position where we're less at risk for a linkage error. Anyway, we're going to go ahead and make the substitution. So we have the 2 on the outside. We have the 1 plus root x cubed, which is u cubed. We have the 1 over 2 root x dx, which is du. And the thing we're going to do now is just transform the limits of integration using the same relationship between x and u that we used to transform the rest of the integral. So I'll ask myself the question, if x is 1, what's u? Well, it's 1 plus the square root of 1, also known as 2. If x is 4, what's u? It's 1 plus the square root of 4, also known as 3. And if we didn't make any errors in transforming everything from in terms of x to being in terms of u, these two things should be equivalent. So let's go ahead and evaluate. We've got the 2. We anti-differentiate the u cubed. We get 1/4 u to the 4th. And this is from 2 to 3. Now, here's the beauty part, if you like to save effort. We don't have to go back, as we did in the previous method. We don't have to go back to writing things in terms of x. We can just carry this thing out to a conclusion. 2 times the 1/4 is a half. I'll factor that out. I've got 3 to the 4th, which is 81, minus 2 to the 4th, which is 16. This is 65 halves. And we save ourselves the trouble of having to go back and re-express everything in terms of the original variable of integration. We can just finish it off, secure in the knowledge that if we haven't made some kind of boo-boo, these two integrals are equivalent. We might as well evaluate the simple one. And here's one more example just for kicks. It is the integral from root 2 to root 3 of x e to the x squared dx. And we once again have a situation where there's a composition in play. And so we should consider substitution. Doesn't always work out, but it's a thing you definitely should be running through as part of your list of tricks as you approach integrals of this kind. So we have an x squared plugged into the exponential function. Its derivative is 2x. And except for the constant 2, which we can engineer at the cost of a 1/2, we have the derivative of that x squared as a factor in our integrand. So let's let u be equal to x squared. Du is 2x dx. And this is 1/2 integral. The 2x dx, that's all du. E to the x squared is e to the u. There are tougher integrals, I have to tell you. And then what about the limits of integration? Well, if x is the square root of 2, then u is the square of the square root of 2, also known as 2. And if x is the square root of 3, u is 3. And now we have this all in terms of u, and we can just crank on it. We got the 1/2, integrate e to the u, you get e to the u. This is from 2 to 3. Factor out the 1/2, we have e cubed minus e squared. If you're following the usual progression of integration methods, this would have been something that probably would have been very daunting to you not all that long ago, and yet now you have the tools to address it in a way that reduces it to something that's really rather simple. So if these things come to you with the right sort of chain rule structure in place, potentially you can render them from being rather forbidding to rather friendly. I hope this is a method that will help you successfully to evaluate integrals as you go forward. Happy mathing.